So hello, everyone. My name is Ian Lee. I'm a postdoc at Flatiron, CCA, and also CCN, which is a new center, Center for Computational Mathematics. I was a postdoc here, and then today I'm going to share with you projects that actually originate from here that is based on this paper and some following up works that we're working on. We got some media attention that this paper was selected as best of 2019 articles by physics.org. So the current and future surveys are going to provide a wealth of information to constraint cosmology, but it's also posing challenges to modeling and thus this workshop. And the challenges are whether our model are accurate enough to resolve down to the small scales that the survey can resolve, and at the same time whether they're efficient enough to be able to model the whole volume that the survey is going to capture. And at the same time, because of the efficiency and accuracy, there's always a trade-off that accurate models for hard problems, accurate models are usually slow, and slow models, less accurate models are faster. So typically to solve a structure formation problem, we have two approaches. The numerical approach is to do simulations. And for cold dark matter, it follows a seven-dimensional collisionless Boltzmann equation, also named Vlasov-Poisson equation, that sometimes we approximate in 4D, also named n-body simulations. So some of these simulation is numerically infeasible on current day computers. But even if we do 4D, it's still sometimes very slow because we need to resolve all the mass and spatial temporal resolutions. So numerical simulations can be expensive. Alternatively, we have perturbation theories. And perturbation theories are great in the sense that we understand order by order what's happening. So every term would have a physical interpretation, but at the same time, it may break down on small scales. So in the linear regime, in this case, we'll have the Lagrangian perturbation theory when we sum up orders by orders of the displacement of particles. We hope that we can converge to the true answer. But on small scale at late time in the nonlinear regime, that's not going to happen. And the high order corrections are going to be as large as the leading orders or even larger. So it doesn't converge. So now we have a competition between the two methods. One method is accurate but slow, and the other is fast, but it breaks down on small scale. And a natural question is, why can we have a model that does both? We already know the answer. The answer is we can do emulation. And in this talk, I'm going to show you how we do emulation with machine learning at field level. So machine learning is a huge umbrella term that covers so many different techniques. Its particular strength, one of its particular strengths is the so-called supervised learning, where you have the input and the target data, and you want to build it. I guess it's cut. So you want to build a neural network to connect the input to the output with layers of hidden neurons, where each neuron is a biological analogy, is analogy to the biological neurons that looks like this. And numerically, we want the neuron to take all the input from previous neurons and linearly form a linear combination before activated with a nonlinear function. The nonlinear function can be anything. Here are many popular choices, but the most important thing is that given under certain conditions, and if the activation function is monotonic, you can have something called a universal approximation theorem that this thing can approximate any continuous function. And now, let's say we're dealing with some data with a spatial structure such as an image. We can simplify the neural network here. Instead of connecting every neuron to every other neuron, we only connect neurons that are neighbors. So from previous layers to the next layers, we're forming a convolution in this case. And within each layer, we can actually have multiple images. So in this example, in the previous layer, we have 3 images. And after we combine it with the 2 different sets of filters, we arrive at an image with 2 channels. So we have layers and channels and neurons. When we combine everything together, we have a deep learning model. Here is an example of a deep learning model with the 3 layers, 3 hidden layers, that turns one image with RGB channel into another image. So when somebody mentions they do deep learning, they simply means that they have multiple channels, multiple layers. Now this thing has many interesting applications or important applications, for example, driverless cars, and then remote sensing. A very interesting application here, it's a very popular app last year. It's called Face app. For example, if you want to check out what it will look like in a different style before commit to it, you can play with it, play with this app. Or if you want to look at yourself at a different redshift, or if you're feeling particularly adventurous, you want to look at yourself if you're born the other sex, you can also do that to go the other direction. So now, since such a black box can turn can dial the clock for a 2D image of a man, it's not hard to imagine that it can do in a 3D for a box of particles or a universe. So the way we do it is simply so they're using a square here. So we simply have training data of numerical simulations with its input and output. We keep updating the parameters in this deep learning black box until we're satisfied with the residual. So we're doing a stochastic gradient descent to training our deep learning model. And the training data, we have two versions. In the first paper, we use actually a PM simulation, fast PM simulations with 128 megaparsec box. And each box only has 32 particles. So it's not a very big simulations, and it's of very low resolutions. And in the recent work in progress, we update this data set with gadget simulations. So it's a 3 PM full embodied simulation with a large volume and also many more particles. So most of the paper, the main results in this talk has been updated with the new data set. So what's in the black box, where you cannot see the input and output there, but here mainly we have been playing with these 2 neural network architecture. One is called UNet, the other is VNet. I won't go into details, but if you want to know more, please talk to me. Yeah, okay. So I want to spend more time on talking about how we design, like with the physical consideration, how we design our network. So so one option we made was that we use a displacement field as the input and also as output. So a very naive choice, or a very simple choice, would be use the density field. But however, in neural network, particularly a convolutional neural network, if you look at one pixel from a later layer, if you look back, it's impacted, for example, from the previous layer, in this case, 3 by 3 pixels. And if you look at further back, it's from a patch of finite size. So we know that gravity is long range. If our final output, let's say, if this is the density at a particular location, if it's only affected by density of a finite volume, that certainly doesn't make sense. So, but on the other hand, we know that the displacement field is non-local. So with a non-local field, even if the receptive field is finite, we can actually effectively aggregate information from the whole box. So that's why we use a displacement field. And in practice, we put the X, Y, and Z direction of the vector field into 3 different channels, just like an image has RGB channels. And a second consideration is that we're actually using the linear field instead of the initial condition of the simulation as the input of the deep learning box. So the previous picture was kind of misleading. In practice, in this analogy, we use the leading order perturbation theory as input, and the deep learning model simply non-linearizes this vector and trying to predict the final position of or the displacement of the particle. So you can think of the black box as a non-linearizer of your linear field. Yes, that's what I mean. And on the other hand, we also predicted the velocity. So in the velocity case, we use the linear velocity as the input. So it's rescaled by f and h. Yeah. For our data, so the physical embodied system has rotation symmetry, but in the simulation box, it doesn't have the full rotation symmetry. It obeys a symmetry that's called by this point group. It's a point group of 48 elements. That means let's take a simulation and we can do any of these performance operations and still maintain the cubic geometry. For example, let's take the body diagonal and rotate it by 128 degrees. We get a new simulation. We can use it as a completely new simulation to train the model. And finally, CNN, or convolutional neural network, has translation invariance. But if we take it simply, usually machine learning people will zero pad it to maintain the size of from the input to the output. When you do zero padding, that breaks the translation invariance. And the solution is to either do periodic padding or completely disable the padding. So in the first version, we did this because our simulations are small. And now with the large simulation, we're doing the second version. And finally, let me show you the results. Okay. So on the left, the point cloud shows the position of the particles, and the vectors are showing you the displacement field from their original positions. And this column is ZA, and then 2 LPT, and finally the deep learning prediction. And the color shows the error on the displacement. As you see that the error is big at dense regions, and this error reduced in second order prediction theory, but it's still kind of obvious that it's pretty big in the dense region. While in the deep learning model, that's not very visible. So beyond point-wise comparison, we can look at power spectrum. And here is the density power spectrum. And perturbation theory means 2 LPT, but other perturbation theory will have a qualitative similar behavior that they will not capture the nonlinear density enhancement there. Now, let me overplot the machine learning predictions. It's almost on top of the simulations. And this is done with only 2 simulations. So each simulation is 1 gigaparsec, 512 cube particles. So with 2 simulations, we can train a neural network to do that. And let's look at the ratio. And the error is not that satisfactory. It's about like 5% up to k equals 1.5. But remember, this is only 2 simulations, and it's very preliminary results with further tweak in the architecture. I think I can further reduce this error on the amplitude. On the other hand, we have the cross-correlation coefficient. And here I'm showing the 1 minus r squared, which is the stochasticity, where you can think of it as a fraction of noise. So the machine learning model actually is at least a factor of 2 better. And again, this is done with 2 simulations with 200. I can further reduce this to below 5%. Now, when we combine everything together, we have the power, ratio of power, and the stochasticity. When the ratio of power goes to 1 and the stochasticity goes to 0, the prediction will be perfect. So on both benchmarks, this is machine learning is doing much better than the perturbation theory, and the further improvement can be achieved when we train it with more simulations. And finally, this is also the momentum or the density weighted velocity power spectrum, because we want to predict observables in the redshift space. So we look at the k-squared power spectrum, k-squared weighted power spectrum of the momentum. And again, the ratio of power looks very good. And again, the stochasticity can be further improved once we tweak the network a bit and then also use more training data. I'll skip this. So our model is very promising in terms of accuracy. What about the efficiency of the model? So on one hand, with one GPU card, a simulation of 1 gigaparsec by 12 particles would take about 1.5 minutes. So the same simulation took 500 CPU hours to perform. If we take a CPU node with maybe 24 cores, that would take about 20 hours wall time. So in total, if you compare one CPU node to a GPU card, that the speed up factor is about 500 to 1,000. It will take, if I use multiple cards, then it would take 1 day or 2 days. Yeah, depending on how many cards you use. Yeah. So to do this, I wrote this code that it's called map to map. It's a very general framework. Let's say if you have some data that takes some arbitrary list of fields to another list of fields that's correlated or has some causality relation between them. This code will help you to train it to take one from the other, basically transform one to the other or emulate. So it has list of features. For example, it has a VM written inside, and I hope it will ease the technology gap to use CNN or to train on CNN. If you're interested, I'm happy to share and add you to the repository 5 minutes. So so the model is accurate and also efficient, and then that means it's a very promising tool to follow model the structure formation at field level. So first of all, I've shown you that the density power spectrum comparison shows that we can solve the gravitational instability, and also showing you the velocity prediction is pretty accurate. And something we haven't done yet is to predict either halos or galaxies, and also include the dependence on cosmological parameters. So that's what we're going to do next. So we're going to use the Quixote simulation that Chan just mentioned. So it's a great data set, and part of it has a Latin hypercube sampling of a parameter space spanning over 5 dimensions and the second data set has an even bigger, more parameters, including potentially neutrino and W. So with these, we can train a forward model with a CNN that takes the linearized field, cosmological parameters, and make potentially some nuisance parameters to predict directly observables and apply systematics and so on. So all of the previous talks have been talked extensively about how forward modeling is going to be a great tool because it's easier to include systematics, apply masks, and you can also include all kinds of physics that you want or you trust. For example, if you have a modified gravity model, and it will be very hard to do it other way. But with the machine learning model, you can simply just use the same exact model and train it on the modified gravity simulations. And then you'll have a forward model for modified gravity. So that brings me to the summary. So we have developed a black box that can interpolate a nonlinear structure formation with a comparable accuracy comparable to the simulation that you used to train it, up to around 1, and it's 1,000 times faster. And in the future, we want to include dependence on cosmological parameters, biasing relations, or alternatively galaxy formation parameters, or alternatively subgrid physics parameters to do this emulation. And we hope that it will be able to constrain both cosmology and galaxy formation at the same time. And that's everything. Thank you.
Maybe one quick question for you. Back. How fast do you
that's about so for this one CPU node to one GPU card comparison, that's about a factor of 5. 50%, 1% what? Stochastic. Yeah, that's something we can further optimize. Yeah. I'm saying that I'm only using 2 simulations right now. But with 200, that's percent lower. Yeah, agreed.
All right. You use 250, right?
Yeah, right.
No matter what you do, it's going to be the best if I get 2 times better than 250.
You mean the input?
The 250 has a cost too.
Right. I mean, but that's the best you can do. So it is not slow. So yeah, our input is actually our input is actually Zolovich.
All right, we need to move on. You can ask questions.
Okay, so good afternoon, everyone. My name is He Jia. I'm a senior undergrad at Peking University with work at Berkeley. And today I'm going to talk about some novel Bayesian methods for the upcoming cosmology service that can be orders of magnitude more efficient than traditional methods. So our starting point will be the Bayes theorem, which defines the posterior and evidence from the likelihood and prior. And as we know, the 2 main tasks of the Bayesian analysis will be the posterior and evidence. So we will present one algorithm for each of the tasks. Now let's first look at the posterior. As we know, if we want to get information from the posterior, we usually need to get samples from it at the beginning. Well, standard method for this can be MCMC, which is, however, slow in higher dimensions because it can require millions of evaluations in a few dozen dimensions. And another standard method can be nested sampling, which is comparable to MCMC in terms of speed. but it can also give the evidence. Well, on the other hand, we will present a novel pipeline for both posterior and evidence, and we will show that it can be much faster than the traditional competitors to achieve the same level of accuracy. So let me introduce our proposed method. For the posterior, our starting point is we observe that usually we can write the likelihood as a composite function of Lm theta. Here, M is some expensive model. For example, it can be the CMB power spectra for the Planck likelihood, or it can be the 2-point functions for the dark energy survey likelihood. And L is usually some simple function form. For example, it can be the quadratic Gaussian likelihood for the DES. And our strategy is we can approximate the expensive model M theta with some simple surrogate functions. And in practice, we found that usually it's enough to just use some quadratic or cubic polynomials for the most cosmology examples. So in this way, after replacing the true expensive model with some quadratic or cubic approximation, we are obtaining approximate density Q theta for the original true density P theta. And then we will run the sampler on this Q theta. To be specific, we will use the low-Newton sampler LUTs to get the samples, which is a special variant for the Hamiltonian Monte Carlo. And in this way, we will get the samples for Q, which is in principle different from the samples of P. But as long as the approximation is good enough, it will not be very different. But nevertheless, if we want to be more serious and if we want it to be asymptotically consistent, we can just add an importance sampling step to which will assign importance weight P over Q to each sample. Because P and Q are usually very close, so we do not need many samples to do this importance sampling. And we observe that it's usually enough to use about 2,000 samples. So let me show you the results. The first one is for the DES likelihood. And here the blue contours are from multi-last. And the yellow and red ones are from our base fast. And if we do not activate importance sampling, we will have the yellow one with 500 evaluations. Maybe it's not so bad. And if we activate importance sampling, we will have the red one, which requires 2,500 evaluations, and it is almost identical to the blue multi-last, requiring 250,000 evaluations. So our method is 100 times faster than multi-last, but it can give the same level of accuracy. The second example is for the 9-dimensional Planck likelihood. And here we are using the stereo neutrino model for the likelihood. The blue one is from MC using 100,000 evaluations, while the red one is from our base fast. Here we did not activate importance sampling because we think it's already good enough. Actually, it's perfect everywhere except for perhaps here the 2 sigma contours. But we think if we want to fix this, we can just add the importance sampling. But we think this is probably not necessary because, for example, the 1D modulus are already very close. So we only need 300 evaluations here, and it is 300 times faster than MC. So this is for the posterior. Now let's move on to the last topic, the evidence. As we know, the Bayesian evidence is defined as the normalizing constant of the unnormalized posterior, and it is widely used as the standard rule for model selection in Bayesian analysis. But its evaluation is also tricky in high dimensions because the naive definition will require the high-dimensional numerical integral, which is invisible. So our proposed method is based on bridge sampling, which originates from the following identity. Here, the P is the target distribution, and Q is some arbitrary proposal distribution. Alpha is some arbitrary bridge function. And this identity says we can evaluate this integral with two different ways, either using the samples from P or using the samples from Q. And here, if alpha is 1 over Q, then it's just important sampling. So important sampling is a special case for the bridge sampling here. And however, we point out that theoretically, we can construct some optimal bridge function alpha in the sense that the relative mean square error of this evidence estimator is minimized. Well, I'm not going to cover this topic here. If you are interested, you can find it in our paper. And besides alpha, we will also need to choose the proposal distribution Qs as here for the bridge sampling. And this is our main contribution for this topic. We propose that since we assume we already have the posterior samples before we evaluate the evidence, so we can approximate a density from these posterior samples, and we use this approximate density as our proposal. Because we will have the normalizing constant of this approximate Q. So from this identity, we can compute the normalizing constant of P. So to approximate the density, we develop a lower normalizing flow-based density estimator, which we call iterative neural transform. I will only cover the basic idea here. So the idea is given some target distribution and its samples, which try to Gaussianize this distribution with some bijective transform. And we require this transform to be bijective so that after we Gaussianize it, we can obtain a density estimator in the original space by computing the Jacobian of the transform. So and then we will use this estimated density as our proposal. And the way we Gaussianize it is at each iteration, we try to find the most non-Gaussian 1D directions, and we Gaussianize this 1D directions with 1D transforms. And then at the next iteration, we find the new non-Gaussian directions, and we Gaussianize them along the new directions. And we have several iterations until we think the overall distribution is Gaussian enough. So let me show you some examples. We have 4 examples in our paper, and here is the last example. It's a 64-dimensional toy example, which has a strong ring-shaped nonlinear degeneracy. Maybe I should show you this. So we compare our proposed method, GBS, Gaussianized bridge sampling, with the other popular methods. And during the experiment, we try to make every estimator use the same number of evaluations, except for this GBSL, Gaussianized bridge sampling net, which means it only uses 25% evaluations relative to GBS. And for this density sampling, we are using the default settings in the density package. So it seems to have used much more evaluations than the others. And here is a comparison of the accuracy of the non-evidence. And it is clear that our proposed GBS is orders of magnitude more accurate than the other traditional methods. And even if we only allow it to use 25% evaluations, it is still much better than the other methods. So the 2 algorithms for the posterior and evidence above will be distributed in a publicly available BaseFast package. And we will also develop a CosmoFast package, which will provide several commonly used functions for cosmology applications. For example, we will have a native implementation of the plug likelihood code. So it's more convenient to use together with BaseFast. And about code, I have already finished all the underlying algorithms, but however, I haven't finished the public interface and the documents. So maybe I will need about 1 month to prepare for the first formal release. But as of now, if you are interested, you can find a Jupyter notebook to reproduce our PES example in the BSFast GitHub directory. So that's all. Thank you.
You mentioned that I missed it, but in the BaseFast, the first algorithm you described, how do you get an accurate Q?
Well,
Like it was like the third slide.
Usually our starting point will be the Laplace approximation. So you find the maximum of the likelihood, and you expand it to the second order at the maximum point, and you get some samples from it, and you use these samples to fit the polynomial model for the polynomial model, and then you can sample this new model, and you can get the new samples, and you can update it with the new samples. So you will need maybe a few iterations, maybe 2 or 3, and then you will be more and more accurate.
Question? Let's thank you then. So the first one comes from Urush, which is based on the talk in the morning. That are we actually getting consistent sigma constraints from different perturbation theory based approaches, and especially the ones using BOS, the ones that have been applied on BOS data. So this is a plot that Byung-Hee made today afternoon with different BOS results. So I think most of them are published, and these are the new results from Byung-Hee's paper, which do give smallest constraint. So Urush, do you want to start the discussion?
So, yes, what we heard this morning was the theory, so that the BOS measurements are low compared to prime. That's maybe one thing we're discussing. The second thing we're discussing is, are all perturbation theories actually equal or not? Is there any difference between the new generation of perturbation theory methods versus, let's say, the old generation, which was used for BOS analysis?
So BOS versus Planck and new generation of perturbation theory models versus old ones. Does anyone want to comment?
This is more on the data side, but it's intrinsic alignment very sure. No, okay, but for BOS, okay, because we measure the data, but it is true, and
So yeah, so the paper is not out yet, but what the model we have seems to predict that it should not, like the intrinsic alignment should not really be a big problem. And that's at least based on the methodology using fundamental plane. There's a whole separate question about whether you trust fundamental plane for that kind of measurement or not. And I don't really know the answer to that. That requires some more work. But based on our analysis using fundamental plane and intrinsic alignment, what seems to be a problem.
but then you say it with the with the statistical arm parts of data.
I mean, we haven't done the predictions for test itself, but you know, the biases we are getting, it's probably like factor of 10 less than BOS error bar, so it should be okay for that.
But you have scaling of intrinsic alignments with something like color or not, and you can marginalize it out.
Yeah, so that's the other thing that we don't have a perfect model for intrinsic alignments, but we have a fairly decent model for intrinsic alignments, so we can always measure it and
one thing. So what I mentioned at the morning talk is that we get lower values of sigma, not f sigma. F also includes omega matter, and so I said the values that we get, assuming the lambda CDM model. So there's a difference between these values, right? So in the first set of the BOSS 2016, 2017 results, all are marginalized over the alpha-Pachinski parameters, assuming they're completely independent. So this is a very general analysis. Then you can see what is the constraint that you get on F sigma 8 if you assume that the alpha-Pachinski parameters and F sigma 8 must be consistent within the lambda CDM framework, and then the error bars are smaller. But so I have here the values that I thought were going to be added to this plot. But so if you look at the low redshift bin and the high redshift bin separately, assuming a lambda CDM, the result that we get at 0.43 for F sigma 8 in the low redshift bin, and 0.4 for in the high redshift bin. So these are still in the bulk of results, right? So
those are still a bit lower than Planck prediction, right?
0.43.
Yes, Planck is above 0.45, right?
So it's 0.43 plus minus 0.04.
Okay, so low Z is.
But there must be a version of this plot that includes this.
0.40 is the same as the interval.
Yes.
So, and high Z is. So you were also quoting the high Z values?
Yeah, the high redshift value is 0.4, also with the same error, 0.04.
So they seem to be still a bit lower than. Okay, another thing to notice in this plot is that your F sigma 8 is roughly omega matter of 0.5 sine sigma 8, which is very similar to what you get from lensing also, which is also low.
It's a different omega n.
I mean, that's
One is
normalization.
redshift 0, the other one is redshift.
Yeah, let me comment on this redshift 0 by the way. So this is the combined CMAS and LOZ, and since it's the combined, we decided to go with the redshift 2. It's not only to extrapolate.
But also, if you do the analysis and try to see what is really the tension, so I didn't look explicitly at F sigma 8, but we did this and the posterior distribution, including all the parameters. Planck and BOSS are consistent between 0.7 sigma. So this is not significant tension.
So the official number is within like 0.7 plus or minus 0.05 or something.
Yeah, something like that.
So they are consistent, more or less.
Yeah, 0.76 plus minus 0.05 sigma. That's yeah. This is but this is so it gets more interesting when you say, well, there's no we get constraints from this not only from BOSS but also from this other low redshift measurements from lensing surveys, and then the joint sigma that you get from all these different.
So with kids was, I think it was like 2 sigma.
With kids is 2 sigma. 2.1 plus minus 0.3 sigma. Yeah, so still, and kids from all these lensing surveys.
What are you saying right now?
So we're just right now quoting the numbers that if you just take only BOSS versus Planck, they're both more or less consistent, like the numbers they got of discrepancy of like 0.7 sigma. And if you include lensing from kids, then it's roughly 2 sigma.
So
that's always on in space?
I
no,
think that's
this is
in omega matter
the
sigma.
full lambda CDM parameter space. And so if you constrain the parameter space, this is and looking at the full posterior distribution of all the lambda CDM parameters, this is the level of the tension. So this is not just including, just considering sigma 8 or f sigma 8 or anything, this is full posterior distribution.
Okay, so I think you also had NS and H.
Yes.
So that's using suspiciousness.
This suspiciousness, yeah. But also, maybe the lensing experts can correct me, but I think that Higgs is the survey that maybe is most in tension with Planck. So it's like the most extreme combination if you combine both with this. I don't have the number.
TSS. That's our results. But,
For stage 3 surveys, jazz is more consistent with Planck than Higgs.
Yeah, that's true. Yeah, so exactly. My statement is use Higgs is the most extreme example, and using the most extreme example is a 2 sigma.
well, I think so. The caveat to that is that it also has larger errors than the ES. So maybe if you combine with the ES, the tension might be larger.
Yeah, we can see.
Maybe comment on maybe a comment that if you come from the 3D community, I mean, this we know that now this is a tension in the ES. Estimate is a function of Hubble, Megametal, and the ES. And we know that it's just a ES that is low. Maybe not significantly lower given that there is so many parameters to the 3D, but the one which is lower than Planck is the ES. So,
No, it could be omega matter.
no, we measure omega.
No,
There's an error, maybe it's 3 sigma fluctuation in omega matter.
Omega metal gives it. I don't know. Omega metal is
Planck gives, supposed to omega matter, 2 omega matter is lower than Planck. This will bring actually down.
so we measure. I don't.
you get a low
Hmm? No, it's very close to Planck.
like lower, but I mean,
No,
this is all driven by the difference, by the difference of sigma and GC basically with respect to Planck. It's like almost 2 sigma away. So in that sense, it's a yes, which is lower than Planck. But yeah, basically this is okay. It's a bit low.
This logarithm of N is 2.7.
Yeah.
3.3.
Oh, yeah, it is much lower. Yes, it's much lower. Yes, omega is kind of like this.
Everything is more, I think, maybe at most 1 sigma lower, right? Yeah, but
So
there
if
is.
we need omega, we need to combine to get omega.
No.
Or BDN.
And then again, you don't trust the end.
You don't trust me.
It's strong. Dopo le puoi vedere qua, because per esempio, tipo decay da meta, no, mega meta è vicino. So, it's important to split.
So I guess the conclusion is that
plus EA of the same component as
Yes.
that's slightly driven by AI.
In other words, it's not an neutrino mass. It's not that you have a big AS and then you put a large neutrino mass that goes, that puts F sigma 8 over this, right? The story is not that we are not detecting the neutrino mass. Really, we're seeing the tension in the primordial amp.
You can ask us if does not have. You cannot.
Yeah, the neutrino mass does not help. Yeah, this is the answer.
Within 1 sigma, omega is flat. Slightly lower than 1 sigma.
Try to explain 2 sigma.
So what no, but if you look at the AS, it's for something similar. AS.
So the error is omega is 0.1.
3%.
Yeah, 3%.
The same.
Point of view, depending on the trial.
So this with BDN.
Will be the end is 3%. Yes.
We will bring down by 2%.
The error on AS is 19%. And this is
Okay, so I guess just one line summary is that the tension is still at maybe like 2 sigma level-ish, but not super significant, and likely driven by AS if you trust the BBM results. So moving on to the next question. So new perturbation theory models versus old perturbation theory models. So I'm not really sure what Russia's question is here.
I mean, different perturbation theory models agree with each other.
Right. So
This
I
model
guess
suggests they all agree with each other. They're all within kind of 1 sigma.
they're all within 1 sigma, but they're all using the same data.
That's a good thing. Right? I mean, the difference is only the perturbation theory, not the data.
Yeah, yeah.
Well, these are different ways of slicing up the data. I mean, it's Fourier space, configuration space, wedges, multiple.
These are all bars.
Go with it.
No. For spectrum configuration space.
I mean, for the Fourier fault analysis, we did one of each.
Yeah, so I think the subpadiatonal was in real space.
Yeah, I think this is a good aspect to emphasize. That given this data, we can use these different tools that are available, modeling tools, and we can get the same consistent constraints. So this speaks about the robustness of these results. So these are not driven by the use of a particular recipe or a particular.
Right, so I guess that's the question here, right? That do you think these are consistent or not? Right? So it's true that there are some differences in the analysis, so it's not really clear that how much of this is just driven by the fact that you're looking at different like data versus just driven by the model.
So this Alam et al. Is just a combination of all the others.
So this one?
Alam, I can see the colors.
I think it is this one likely.
Zero.
There was a question. Yeah.
I'm not talking about the agreement. After a little share, when I did talk with us motivated as in going too further. So I think that in our analysis, the strong effort to compare with challenge simulations, and we claim that the systematic error from theory, which is less than a quarter of a sigma. So according to this, the perturbation theories should be within a quarter of a sigma, not within a sigma. Very high, very high level of theory.
There's different data going to this. So we use hexadecapole, we use up to 0.4. So there are differences.
Yeah.
But the reason why doing this challenge is a good thing. We can fix data. And also, big volume is good to resolve the issue. Because here, of course, everything agrees because the error bar is so big. It would be good to set up one example where you don't know the technology. Keep smaller bars and see what comes out. It's the only way to see whether there is really some reasonable difference.
Right. So I guess we need like
single space, free space.
mock challenges or something at heavy volume.
Lauren, do you have anything to say about mock challenges? I'm guessing you talked.
Yeah, I'm gonna stop with you.
But do any of these challenges be publicly available?
We can discuss that tomorrow.
Yes.
also very scale the whole thing to match the both covariance.
And you took things that we had there.
No, yes, we do
Yes.
yesterday.
How does the fluctuations of parameters? What's the covariance matrix question or the model question? No, thanks. It's both. It's both. Sure. Yeah. If you've got interesting degeneracies in the model, they can compete against interesting errors. Theoretically, it's hard. Practically, it never is. Theoretically, you can blow things up at a condition number of things fast. That never happens. Everything is compatible, I remember, but there were small fluctuations. Of course, it's expected that different boxes were different. But if you combine them, it was the same.
So we did this comparison on all the box analysis. So we used the Minerva in our case, but also this Cascade modes. And when we look at the distribution of the best fit values of the individual derivations, we put a histogram of that. They match very well the posterior distribution that you get from fitting the mean.
Okay, so any more comments on this? So, okay, so we can move on to the second question.
Maybe one comment on that now. Just
Yeah.
It's not just estimate, right? A new thing is that also you measure everything, apart from maybe priority and because all new versions of I mean, now knowledge of control on everything, you get everything applied, not just estimate.
That's BAO.
Well, it's a shape.
That's the problem. It's only the problem. It's not the shape of the process.
I think I've many times. I think both. All operations estimate and the BAO. So if you disagree with that, show us the proof. Right? That's not true.
But the proof is that if you take the power spectrum, which there's no weakness, no delay. And you generate the mock data, which looks like the same current in the boss. Don't demand on that. You don't need
Much worse than with the BAO. It's not relevant.
But if you do the same thing, okay, for both here, this is true. It will be worse. Like H0 will be twice worse on the method cost. But in the future, if you do the same exercise with the Euclid for you, then there will be no difference. So you remove the BAO completely, do the same result. You measure omega matter as good as would be. I don't know.
If you threw in lensing also, then I think that's definitely true that you can measure omega matter competitively.
Also,
that's
one
one
periodic step. It's
not even really that, no, because I mean, if you look in like a DES like analysis, we're not really sensitive to those scales anyways, and we can strain omega. So.
No, that's just because sending is
Sure.
But what is the problem with even using BAO? I mean, before before we were using only BAO and then play with it. Now, like, no, because you say, oh, the information has to be
No, the problem. I mean, the point is just that because for reconstructed BAO, it's not a process. In other words, it's much more information in reconstructed BAO than shaping the process.
No.
Yeah, we'll get to that.
Okay, so yeah, the next question was more about using perturbation theory based models or using simulations going down to very small scales. And I think the question really comes down to is how well do we think we are modeling galaxy physics, and how much information are we actually gaining from small scale? And it's true that if we really need to go to small scales, we need something like emulators or some other simulation-based approach. But the question really is are we really going to get any information? And my understanding from hearing the talks today was that modeling of galaxy physics is still kind of a work in progress. So it's hard to answer this question, but yeah, let's just discuss. Joe?
Yeah, this is a hard question to answer, but I think at this point, yeah, I would say I don't really trust any of the models that are going down to like the very smallest scales. I think there are a number of tests that still need to be passed for those models that haven't really been passed. One is looking at hydro simulation, trying to. The problem is that we don't really have realistic data sets that we know the right answer in large enough volumes that have more complexity than the models that we're already using. So, I mean, Jeremy was talking about looking at using HOD and comparing to sham, but I mean, there are also effects that you worry about from baryons and stuff like that, and there you want to go hydrosim, but the hydrosim volumes are just not big enough. And so,
well, I somewhat disagree with that, right? What you want is a model that's able to handle whatever data signal you're actually handling, right? It's just bias. And so you can have some model that's got subhalos, right? That's the thing you want some subhalos. Because you want to break all the HOD assumptions. And if you can tune these abundance matching parameters, and I guess put orphans in or have do something to try and correct that. But it doesn't have to, and then just hand the model some data that's got a wide variety of clustering predictions based upon different knobs that you're tuning. And if it always comes back with unbiased cosmology parameters, then you're good. Even though you don't know whether or not one of these models is the right model, but it's got the right Gauss information. As long as you're spanning a wide range.
So but you're still there assuming you're still assuming that the radial distributions of subhalos follow dark matter. So you're assuming basically that you're able to marginalize over whatever baryons are doing to the actual dark matter profile by incorporating some concentration dependence or something like that. So which I think hasn't been shown.
You know the direction of the impact of spurious disruption, right? And that's going to reduce the concentration. So you just do something to boost up the concentration. Like you've got the Dr. Norton's model, which goes in it overcorrects in the opposite direction.
No, but it's not necessarily the case because you have disks in some of these galaxies which could also disrupt more things. It's actually a pretty big effect in galaxies that have disks.
Well, then we know this. So we can.
Yeah, but there's like a million things like that that you could potentially worry about. So,
I mean, this is where I think perturbation theory does give us some value. We think the perturbation parameter is 4 megaparsecs. We think that, in space much larger than that, you just need maybe 1 term, a square or whatever. And we think that when we cross that threshold of those get smaller than 3 megaparsecs, the number of parameters explodes. Nothing. It's non-repetitive, and we just can't say anything. So, whatever you, Jeremy, are saying, I think we throw on zillions of different HOD parameters and marginalize all of them, and then convince everybody else that you get something reliable. Right? Well, you need to throw zillions of them.
I don't know if it needs to be zillions. It's whatever it needs to be, such that no matter what mock data you send me, I get unbiased reviews. So,
there's so many ways to do this. It will take a long time.
Yes,
there's something nice about perturbation theory, right? It's work in the perturbative regime.
I mean, I think there's no question that we can use a perturbation theory-based model on this to get cosmological constraints. Like, we'll be able to do that. So there's no reason. I mean, people are going to work on that. People are going to do it. We'll have those constraints, and in the meantime, we can try to do things that push things further. I guess the question is just, are we wasting person power by that?
Right? Never. I mean, you're saying I'm not going to look at things below a megaparsec, even though I know there's information there
You don't trust the hydro, and your dark
You don't have to trust the hydro.
No, but the dark matter simulation, I mean.
You don't even have to trust the hydro for the dark matter simulation.
So, but then, I mean.
I've been granted zillions of HOD parameters. I can do anything.
Right, but what about
Yeah, but the question is like, given this way HOD parameters,
so I match, but I thought I'm actually matching the model to the wrong dark matter properties. I mean, because dark matter halos are in different places. I mean, there's some halos where some fractions of the not going to exist, not with this disruption within the dark matter simulation, just with the baryons do something different. I mean, some old comparisons, I'm sure they must have known with the lustrous that you get trajectories, you get some halos, some varying places. So if you force your HOD on the wrong dark matter simulation, I mean, how do you know that that's going to give you the right physics?
Well,
I mean,
so I agree that all these things can happen or do happen in different, they manifest in different ways, but we know what the impact on clustering is, and it's not really like I'm going to tune an HOD parameter to get the right result on one model or one simulation. You're going to increase flexibility up and until you don't need to do that.
So, Jeremy, so I guess the question is that if you throw in CD and HOD parameters, are you still getting any like cosmological information out of those small scales?
Well, we have 18 parameters now, and we're doing okay.
I mean, this is the reason why I think HOD is the wrong. I mean, I think for certain purposes, HOD might still work, but I think there's a strong motivation to move beyond HOD, which is in terms of things like what Andrew was talking about, what I was talking about, because yes, you can add extra parameters, but if you're also adding predictive power at the same time in terms of being able to predict other signals, then you can potentially win in this game. For instance, if you can...
These are complementary. You don't choose one of the other.
But I guess my argument is just if you're adding parameters, you want to also be adding predictive power and not just adding flexibility to the model.
So these are the
I mean, that's how I feel.
Question for both sides in the room. So far, we've mostly been talking about putting the precision modeling down to a smaller and smaller physical scale. But what are those sides plans for modeling redshift dependence?
Right.
If you want to move beyond Onion Meta and Sigma 8, the overall normalization, then we're really looking for modulation of redshift dependence. And
so I
if you
think
go with 3 parameters redshift bin, it is not clear to me how those approaches would go there, or marginalizing or altering use functions. So what's the testing scheme there and the way to go forward as we go to broader and broader redshift coverage?
I think that's a strong motivation for having like an evolutionary model based on some sort of simulation, where if you're able to convince yourself that that you have the correct evolution with redshift, which is hard to do, but you can do it by, for instance, I don't know, say you're trying to predict stellar mass space selection as a function of redshift. The thing that you need in order to predict stellar mass as a function of redshift is star formation, right? Or something like that, accretion of stellar mass onto your galaxies. So then at each redshift, you can also look at star formation rate dependent clustering. If that's also correct, then that gives you some way of checking to see whether or not that is a reasonable model for that evolution. Yeah, I mean, that's a hard question because when you split your data up, you're only going to be able to see things at lower signal to noise than what you actually need to predict things at, but it's a potential useful test.
So I totally predict we will not achieve precision homology until we have much better observations of galaxies, how they are actually distributed in the universe. You can have a zillion HOD parameters, it's no guarantee that really unless you actually have data that you can compare your simulations with. Right? So hear more about how you can get that in the paper Wednesday. More than out there. So basically, the real universe is much weirder than what we regular structure. So data will be the ultimate paradigm. What's going on?
Also, in the vein of reality check, I think Roche's point that you might need a lot of parameters for model structure on small scales is well taken. But my question is more basic. Do we have physics reasons to think that the galaxy clustering on scales less than 1 megaparsec actually cares about dark energy or cares even a lot about omega matter? I mean, I'm worried that there's a risk is like someone making chocolate chip cookies where you see the cookies, but by mixing it, you kind of erase this video a lot of the larger scale conditions. How much separation of scales is that?
Just on the omega, so dark energy I don't think really cares at all. So that's why I personally, advertise this sort of stuff that we're doing in Analyses as pro-construction.
Do you think the key question there is GR? Basically, it's GR, right?
Neutrinos also. Yeah, well, yes. As Joe pointed out, we're going to have neutrino simulations next go around, so we'll be able to do that. But so
neutrinos really are quite homogeneous. I don't know if you just say that's a lot of restrictions. I guess I've never.
Well, they wash out small scale power.
Well, but on scales much larger than 1 megaparsec.
it has an impact on a non-negligible impact on the halo mass function, which is the thing that you're really probing in small scale galaxy clusters. So, which is on the omega matter thing, right? In the real space distribution of galaxies, they don't care about matter, but this is all redshift space distributions, right? So, like I said before, you just take every halo in the universe and double its mass, then the fingers of God get larger by a factor of 3 to the 0.5 or 2. So you can probe that.
Maybe I can Simone mentioned what is the key point of view, so maybe I can add my point of view. About, I think before the analysis that was done on loss data about the parameters, the redshift parameters, we didn't use anything. That is, the two parameters, the two redshifts are taken independent, so there is no guidance. And even though there was a lot of skepticism about the fact that the parameters were raised on information, it does not that we can measure both the redshifts, the parameters of both redshifts independently, and you see the kind of consistency you get. So that's very good. Of course, I personally, I'm not the PT versus simulation. I'm together with simulation always. So I would really like. So one thing I think we would like. So we didn't use so far in the analysis of the simulation theory. We never used the information on the bias parameters of the simulation. Okay. Simulation didn't tell us anything about that, and I think maybe we can use something from that. For example, measuring the time dependence as we fit in simulation. Maybe it allows us to, on the data, since maybe we cannot trust much simulation, but we can give us the range of variation and maybe impose some constraints which the function, as a function, will have that time variation so that we can predict, measure the bias and connect the bias. This, for example, getting the time dependence, getting some guidance and trials from simulation is very good. I also asked many times to simulation people if they could give us trials on the bias coefficients. We never use them, but if they can say B2 should be B1 plus B1 squared within 10%, we will use it and we can use it.
Distributions exist. So Alex showed this distribution. So some halos. So you relations of B2 as a function of B1.
No, it breaks down once you put that. There's even an appendix to T1's paper that has HODs, and depending on what you pick for HOD, it's very broad.
Yeah, that's a theory thing that I think is but English is measured.
So I think just to quickly summarize your point that basically you want to have like a emulation function that's motivated by perturbation theory and then that's trained on simulation. Is that the kind of approach?
These two modern words.
think it's even simpler. Just like give us some priors for okay, P1 is 2 plus minus 0.01. It's amazing. We'll measure sigma to 0.1 precision now.
Okay, but how can you get the priors?
Well, they don't want to measure everything in simulation. If they can do that, what I'm asking is less than what we want to do. So, and this is a necessary step if they want to do more.
That's more of a meta comment. I think the framing of this question is kind of unfortunate. Like PT versus sim based, like it sets up this like is it this is like a fight that hashed out, and so of course it elicits comments about like how this method is going to look better at this time. The field is not that big. There's not that many people doing this work. It takes time to improve upon the current state of things. I guess I don't. Simulation-based methods provide validation data sets for perturbation theory approaches.
It's meant analytic.
Yeah, but the methodology that's required to develop accurate emulators is also useful for a lot of other aspects that are necessary for precision cosmology, using perturbation theory or whatever else you want.
Since you say the community is not as big, but it's not a much bigger than the two guys. Come to this conference 1 year ago.
On the data, all of the data have been analyzed with perturbation theory so far has not been single analysis with analysis.
Oh, there have. They're like, well, I guess they're not loss data, but there are emulators. I mean, there's clustering and lensing analyses now.
Yeah, I'm talking about redshift.
Well, Johannes almost has one.
He
actually has a result, he just doesn't actually have it.
Okay, any last final comments? I think we need to end soon.
Maybe one comment on this, Alan. So the strategy that we followed for the final and results from both is that so in all of these different papers we use different statistics and also different models, right? So although maybe they're not that different, we use different modeling. And instead of just choosing then the best one or the one that gives the smallest error, right? We combined all of these results into these consensus constraints, and this was really powerful because it improved the statistical acceptance of the final results. So also, if we just increase the possibilities of models that we can use to extract cosmological information from the data, instead of trying to decide which one is the best one, we should always have in mind the idea of combining all of these results, correctly accounted for the covariances, and maybe this is
sort of correctly account for covariance is harder than it sounds. Right? Easy overfit, you can easily get a singular eigenvalue, get zero error just because you didn't have enough simulations.
Yeah, well, and for most we managed to do it. So I guess
is it believable? I don't know. I'm not sure.
It is.
What do you mean?
You only gave 10%.
10 or 20% means two more years of data.
10%.
10% in the worst cases, 20% in the best cases. This is 2 more years of observation. This is amazing. It is really an amazing. And of course, you should do it.
All right, so I guess we should end here, and I think our main conclusion is that science is long, so we'll keep working on these complementary methods and hopefully we can work on that. All right, thank you everybody, and we have dinner at 6 on 6th floor.